Alright, hello. Welcome to 2004 HSC Physics short response questions. There's not many questions, but yeah, let's get through it. So a projectile is fired at a velocity of 50 meters per second at an angle of 30 degrees to the horizontal. Determine the range of the projectile. So there's actually a formula that you can just use, but given the velocity and the angle to the horizontal, and I'll get you the range straight away. The markers, I think, were quite pissed at that, and what they actually wanted you to do is calculate how long this projectile stays in the air, and then use that time, times it by the x velocity, and then you can determine the range. Anyway, this is just a math question. Just choose your equations, substitute, and solve. Shouldn't be that difficult. Alright, question 17. Okay, so a Apollo 11 command module with Michael Collins on board orbited the moon, waiting for the ascent module to return from the moon's surface. Okay, so we have the mass, we have its period, so the period is how long it takes to orbit, in this case how long it takes to orbit the moon, and the radius of orbit. So assuming that the command module was in a circular orbit, calculate the mass of the moon. So we can just use r cubed over t squared is equal to gm over 4 pi squared. You only have your one unknown, and you can solve for m. Just as you're doing it, try not to make any algebra mistakes. The magnitude of the orbital velocity of the command module. So orbital velocity is equal to the square root of gm over r, where m is the mass of the moon, so we need to use the mass of the moon. Or likewise, we can just use 2 pi r over its period, and that would get us its orbital velocity. Alright, part B. The docking of the ascent module with the command module resulted in an increase in mass, but the spacecraft remained in the same altitude. The docking procedure made no difference to the orbital speed. Justify this statement. Yeah, this statement is correct, because remember that orbital speed is equal to the square root of gm over r, and it's only dependent on the mass of the moon, and not dependent on the mass of the spacecraft. So yeah, this statement is correct. Question 18, we have mass, speed, and radius. So immediately this is centripetal force here. A person observing this situation makes the following statement. There is no net force acting on the car because the speed is constant. That's not true. The speed is constant, but there is a net force. Alright, assess this statement. Support the answer with analysis of the horizontal forces acting on the car using the numerical data provided above. So they just want us to find the centripetal force acting towards the center. Probably 1 mark for saying that this statement is incorrect. Why? Because there's this statement here, no net force. That's incorrect. And there is a net force, and we can calculate it. Yeah, even though that the speed is constant, it's changing direction. So it's a change in velocity, and there's acceleration, therefore there's force. Alright, question 19. On the 11th of June 2003, the Mars rover called Spirit was launched on a satellite from Earth when the parents were in the position shown in the diagram below. The satellite arrived on Mars on the 3rd of December 2003. Indicate on the diagram the approximate positions of Earth and Mars on the 3rd of December and show the satellite's trajectory to Mars. So since this is like half a year, Earth would be halfway through its orbit, so Earth would be up here, and I'm not so sure how long it takes for Mars to orbit, so we can probably like put it about here, and we'll just draw a trajectory slowly coming out to the orbit of Mars. Discuss the effect of Earth's motion on the launch and trajectory to Mars of the satellite. So it's basically saying, why do we have to launch this way? Well, we need to launch in the same orbital in the same rotational motion of Earth and also in the same orbital motion as Earth, because the satellite gains the speed from its inertial frame of reference, and meaning that we can use less fuel, so it's cost efficient. Yeah, that sort of stuff. And we can probably make mention up to there about launch windows. Alright, question 20. The photograph shows a transmission line support tower. Okay, they want us to identify part A's and B. So A is the lightning rod. So it's a neutral wire that gets struck by lightning and is connected straight to the ground. And B is the insulation discs that keeps the wires to the tower and insulates the wires from the ground. It's a describe, so it's okay. 2 marks. Diagram shows a 2-pole DC motor as constructed by a student. There's 3 mistakes with it. Identify them. Alright, so first thing, no power supply. Second thing, coils aren't attached to the commutator. Third thing, the coil doesn't look like it's in this right starting position. And maybe just a fourth thing, just to make sure. The way how it's structured here, it looks like that the coils are going to be going in opposite directions because of this wire here. And remember, if you write something wrong in the HSC, as long as you don't contradict yourself, you should be okay. If you write something wrong, HSC markers will ignore it. But if you contradict yourself, then that's where you can't gain any marks. Alright, an ammeter was used to measure the current through a small DC motor. It's running, so when running freely, 2.09, and then when it was stopped, 2.454 amps. Explain this observation. So when it's running, it's generating back EMF that opposes the current that makes it to run in the first place. And so the net current is reduced, but when you hold it, the coils don't cut lines of flux, or there is no change of flux, and so current is able to run through it freely, and thus the whole current is just 2.54. I'll probably draw a line and then just say observation 1, observation 2. How many marks? 3 marks. So it'd be probably good to make reference to Lenz's law. Oh look, now this time we have an AC electric motor. Describe the main features of this type of motor and its operation. Well, it's AC input. It looks like an induction motor to me. You've got all these coils on the outside, and then you got the axle in the middle. So it just says describe the main features of this motor, and then we're going to need to relate its features to the operation, so probably make reference to a squirrel cage, the coils on the outside, axle in the middle, coils always having changing current, which makes a changing magnetic flux, and then mention Lenz's law, tries to oppose it, so it tries to keep up with it. And yeah, okay. So, in the past 50 years, question 23. In the past 50 years, electrical technology has developed from the widespread use of thermionic devices to the use of solid-state devices and superconductors. List 3 disadvantages of thermionic devices that led to their replacement. So thermi, remember, means heat, and ionic is the ions. So one disadvantage is you had to generate heat, which took time, and it was inefficient. They also had to be in a vacuum tube made by glass. Glass was fragile, they were large and bulky, and because it was a vacuum tube, it was more fragile than usual. So basically just list disadvantages, and then it got replaced. Outline one advantage of using superconductors with reference to 2 applications. Superconductors have 0 resistance. So probably you can just define what a superconductor is. A superconductor is a conductor that has 0 electrical resistance to current. And then 2 applications, they are used in maglev trains and supercomputers. Oh, that was quite a mouthful. Okay, question 24. In the late 19th century, Westinghouse and Edison were in a competition to supply electricity to cities. This competition led to Edison holding public demonstrations to promote his system of DC generation over Westinghouse AC generation. So, okay, this paragraph we don't need to even read. 6 marks, that's important. Propose arguments that Westinghouse could have used to convince authorities of the advantages of his AC system generation and distribution. Okay, so we need this and this of electrical energy over Edison's DC supply. Alright, so we can probably just draw a huge diagram comparing the AC and DC together, but it's not a compare question. DC can't be transformed while AC can, and we also have so we have the use of transformers, which helps distribute it. Generation for Edison's DC power supply, he would need a generator like every 10 kilometers, whereas Westinghouse would only need one big generator, and then he could supply the entire city. But propose arguments, so we need to list advantages over the AC system. No, over the DC system, sorry, that the AC system has, and it's 6 marks. So I'm kind of thinking we're going to be needing 3 main points, and then 3 advantages, relating both to generation and distribution. Okay. Question 25. An example of a solar cell is shown below. Alright. Use this information to outline the process by which light shining on the solar cell produces an electric current that can light up a light globe. So a photon hits the layer, hits an electron. So we can break this up. It's 6 marks, so we need to take this question really seriously. A photon would hit an electron, so maybe we should break this up into 3 parts. Light coming into the system, the electron traveling around the circuit, and then the electron coming back to its original spot. Alright, so and we need to put in as much maths as we can. So when a light's frequency is not comparable to the work function of the material, then the electron is just not going to jump out. So we need to put lots of maths and details here. Yeah, so once it jumps to the N-type layer, there's a potential difference. This would act like a battery, and thus the electron is going to go around the circuit. And this is not one electron, this is going to be millions and billions of electrons. And it's just moving one by one. Alright, the diagram shows part of experimental design to measure the force between 2 parallel current-carrying conductors. Alright, so we have tabulating, so we're probably going to do a line of best fit. Yep, plot the data and draw the line of best fit. 3 marks. Alright, I guess just do your best here. Calculate the gradient of the line of best fit. Remember, it's F times 10 to the minus 6 newtons. So just remember that as you're calculating the rise. Write an expression for the magnetic force, constant K, in terms of the gradient and other variables. So we have F is equal to K, I1, I2, over D times L. And I think what they want to do here is just make K the subject. And then we solve for K. Alright. Question 27. A sports magazine commenting on the athletic ability of Michael Jordan, the famous basketball player, said, "Being an athlete takes more than brains than brawn. It takes time and effort. It takes endurance and commitment." Alright, that's just a bunch of wobble. We don't need that. It takes an athlete who can stay in the air for 2.5 seconds. That's the only data we get. So let's use it. An athlete who knows which laws of physics keep him there. I'm not so sure what to do with this, but I know what to do with this. Assess the information presented in the magazine using appropriate calculations to support your argument. So, if we have the time of flight, we can calculate what his launch velocity was, right? So we can essentially treat Jordan as a projectile. So we're going to calculate his initial velocity, and I don't know what that's going to be, but if it's like 50 meters per second, then it's safe to say that this information here is inaccurate, because staying up in the air for 2.5 seconds is a very hard thing to do. And we can treat Michael Jordan as a projectile because we know he's not a rocket. Like, he doesn't have rocket boots, I mean. Assess the information presented, so we say, depending on our calculation, we say this information is correct or incorrect. And yeah, it's 4 marks. So probably 2 marks in the calculation, 1 mark for our judgment, and 1 mark for our reason. Okay, and they gave us a lot of space. Okay, that is it. Alright, thank you for watching.